here's a great question. Why are nuclides radioactive? And why do they undergo different types of decay? We talked about alpha and beta particles being emitted, and gamma radiation, electron capture, positron emission. Why do some nuclides do this and others don't? Well, a nucleus is a collection of nucleons. And so that's a collective word for protons and neutrons. So these are like the residents of the nucleus, right, the nucleons. And have you ever wondered what holds those together? Because we know that positive charges repel each other. And here we have a whole bunch of positive charges jammed together in the nucleus. That just doesn't seem like it would work. They are held together by something mysterious called the strong force. I'm like, really? You couldn't come up with a fancier name for that, but the strong force. And so this is physics. It's a fundamental force of physics. It acts at very short distances. We do not need to understand what the strong force is. But this is, it's not Star Wars. But it's what holds the protons and the neutrons together. So the stability of the nucleus is a balance between the repulsive coulombic forces between the protons. So protons and protons are repelling each other. And we have the attractive strong force between all the nucleons. So we have this balancing act, repulsion between like charges and the attraction of the strong force. Well, neutrons play an important role in stabilizing the nucleus because they attract other nucleons without contributing to the repulsive force. So you get too many protons, you're going to increase the coulombic force, which is pushing things apart. But the neutrons only contribute to the strong force, which is attracting things. So nucleons actually have energy levels, just like electrons have energy levels. We're not going to talk about what they are. But because they have different energy levels, we get to a point where the energy payback from the strong force, could you get the door? No longer compensates for the high energy state that adding extra neutrons must occupy. So the ratio of neutrons to protons is an important number in determining nuclear stability. So neutrons contribute to the stability of the nucleus and protons work against it. So this is a graph referred to as the valley of stability. So you could think of this as being like a river valley between mountain ranges or something. This is a graph of the number of neutrons versus the number of protons for the different elements. And what we see is that they follow a trend, but the trend is not quite linear, and it does not have a slope of 1. A neutron to proton ratio of 1 is this red line. And so we see that down here it's close to 1. Carbon-12 has that ratio of 1. But as we increase in size, the number of neutrons relative to protons increases. And so up here with mercury, it's up to 1.5. So the green dots are representing the stable nuclei, and the yellow ones represent the other nuclei. And so there's this path or valley through the middle of this where things are stable. There are no stable nuclei above Z equals 83. So that's element, where'd you go? That's bismuth. So above bismuth, all of those guys are going to be somewhat radioactive, unstable. So what kind of radioactivity is emitted by a given nucleus depends in part on this N to Z ratio, because they're going to emit particles that are going to make the N to Z ratio more stable, more favorable. So like one of these guys over here is going to emit particles to bring its ratio over to the green area. So if the N to Z ratio is too high, that means we've got too many neutrons. And so then the tendency is to convert neutrons into protons using beta decay. Because in beta decay, a neutron gets converted into a proton and the beta particle is emitted. If the N to Z ratio is too low, then we've got too many protons and we're going to convert protons to neutrons. And this can happen by positron emission or electron capture. It can also happen through alpha decay, but that doesn't affect the ratio as much. So there's two ways to predict the type of radioactivity. One is to look at figure 20.5. Look at the graph. The other way is to compare the mass number of the nuclide you're looking at to the atomic mass on the periodic table. Atomic mass on the periodic table is an average of stable nuclides. And so it represents an N to Z ratio that is just about right. So example here is ruthenium-112. So if we find ruthenium on the periodic table, where'd you go? $44? Thank you, I was looking too low. 44. Okay, so on the periodic table, ruthenium has an average atomic mass of 101.7. What's the mass of ruthenium-112? 112. That's not a trick question. The mass of ruthenium-112 is 112. This atomic mass is 101.07. So in order for this to be still ruthenium, this must have too many neutrons. And so too many neutrons, we would predict beta decay. So here, N to Z is too high, and so we would predict that that would go through beta decay. That is a general prediction. It's not always true. Okay, predict whether each nuclide is more likely to decay via beta decay or positron emission. So before we look at these, let's just review. So beta decay is going to happen when we've got too many neutrons. And positron emission is going to happen when we have too many protons. So lead-192, on the periodic table, lead has an atomic mass, an average atomic mass of 207.2. So is this going to have too many neutrons or too many protons? Too many protons, because this is lower. That can be a kind of a hard thing to figure out. So we can look at this and see, we can figure out what its actual ratio is, because this is the mass number. That's all the protons and neutrons. And lead is 82. So lead has Z equal 82. And if we subtract that, then we get 110, and that's the number of neutrons. So the N to Z ratio for the stable one is 110 to 82. I'm sorry, the ratio for this particular one is 110 to 82. So 1.34. This is the stable one, or close to the stable one. So here we can just round that to the nearest whole number, 207, and we still have 82 protons. 207 minus 82, 125. So this is protons and this is neutrons. And so here we have 125 over 82, which is 1.5. So this is the stable one, and this is the unstable one. And what we're looking at is, how does it need to change? Pardon me?
The number of neutrons is higher, 125.
Yeah, the number of neutrons is higher here. So we don't have too many neutrons, we got too many protons. To make this a larger number, we have to decrease the denominator, divide by a smaller number, right? Yes?
Why are you subtracting 207?
That's a great question. Why am I taking 207 minus 82? This is the average atomic mass of the stable isotopes of lead. There may be more than one. So this is representing something that's stable. And so 207, the mass of it is very close to the mass number. So something stable is going to have about 207 total nucleons. We subtract the number of protons to get the number of neutrons. And then we can get an approximation of a good ratio for lead. Does that make sense? Well, let's look at lead. Oh, I guess we should write an answer there. So we can look at this one and see, well, its mass number is lower than this one, and so that's going to be not too many protons, and so positron emission. Here, the mass number is higher than the stable one, and so that'll be beta decay. So you don't have to calculate these ratios, but if you can't remember which way they went, then you can calculate the ratio fairly easily, and you don't actually have to remember. Yeah?
This B has a lower number of neutrons?
So this one has a higher number of neutrons relative to the number of protons than the stable one does. And so then we want a decay that's going to get rid of neutrons, so that'll be beta decay. What it does is it converts neutrons into protons. So they're both changing, but the overall effect is getting rid of neutrons. Xenon 114, if we look at xenon on the periodic table, 131.3 is a stable, the average of stable nuclides. Well, now we've made a pattern for ourselves. This was lower than stable, so that was positron emission. This one is higher than stable, that was beta decay. Is this mass, 114, bigger or smaller than the stable mass? It's smaller. So we're going to use this one. That one must be positron emission also. This is not a big deal, but there are some questions, I think, in the homework about it, and there might be one exam question. Magic numbers. Doesn't that sound fun? So the ratio of neutrons to protons seems to be important, but the actual number of protons and neutrons also affects the stability. And what we're talking about here is like general observations. There's not really any, this is more like a law than a theory. There's no real explanation of why this occurs. But we observe that a large number of stable nuclides have both an even number of protons and an even number of neutrons. So if we look at stable nuclides that are even, there's 157 of those. Combination of even and odd, total of 103. Odd and odd, there's only 5 that are stable. So the idea here is that nucleons have a tendency to pair together, much like electrons pair together. You know, we get the spin-paired electrons in an orbital, so that even numbers are better. So nucleons occupy energy levels, and so just like atoms with certain numbers of electrons are very stable, we also have atoms with this magic number of protons or neutrons are uniquely stable. So we looked at, more evens than odd are stable. And then within that group of evens, we see that if N or Z is 2, 8, 20, 28, 50, or 82, those guys are especially stable. If we have the number of neutrons being 126, that's especially stable. So all of these magic numbers are even. You do not need to memorize the magic numbers. Okay, don't bother. It's kind of the end of that. Any questions? You didn't understand. Well, that's fair. So what element has 2 protons and 2 neutrons? Helium, 2 protons, element number 2.
Yeah.
And its mass is 4, so that's 2 protons and 2 neutrons. So helium has a double magic number. It has 2 protons and 2 neutrons. Is helium stable? Yeah. I'm not sure if there are any compounds that helium makes. It just doesn't react. It's super, super stable. And so we could go through and find different nuclides that have N or Z, neutrons or protons with these numbers. And we'll see that those are especially stable. It's just something that people have observed. They're like taking this data and it's like trying to find a pattern in it. And so it feels a little like clutching at straws. But this is what it is.
Just know the element is stable if it has number of protons equal number of neutrons.
If it has a number of protons equal to one of these numbers, or a number of, I'm sorry, that's protons, or neutrons equal to one of these, it's uniquely stable. If it has both, then it's also uniquely stable. And then 126 neutrons is also special for some reason. Yeah. So this is one of those things that I'm teaching you about, but I'm not going to give you an exam question on magic numbers. Radioactive decay series. So we did a problem at the beginning of this chapter where we wrote nuclear equations for, I think it was alpha decay and beta decay and then alpha decay, a series from one nuclide. This is an example of uranium-238 and how it decomposes to eventually become stable. So we mentioned that all atoms with protons number over 83 are radioactive. They will decay in one or more steps. It's mostly alpha and beta decay. Gamma decay comes in when there's excess energy that needs to get spit out. And the decay is going to continue until a stable nuclide is reached. And so what we've got here is the number of neutrons versus the number of protons. And up here we've got uranium-238, and so it's going to undergo alpha decay to become thorium-234. Thorium-234 does beta decay to Pa-234, and then another beta decay to uranium-234. And then it does a series of alpha decays getting down to polonium, and then here it kind of does both, and eventually it's down to lead-206. Lead-206 is stable, and so it stops there. Any questions? As it goes through these, the N to Z ratio is becoming better. These are becoming more stable. Again, this is not something you memorize. Just know that radioactive elements can decay in a series. They can go through a series of decays into different elements, different isotopes. Yeah?
I did a project in a class that was my geology class. We got the abundances of certain elements
Mm-hmm.
in stars to see if they got a certain amount of thorium to see if their exoplanets could drive volcanic activity.
Mm-hmm.
And this kind of reminded me of this.
Yeah, yeah.
Heat from the decay causes tectonic movement.
Yeah, that's a good point. So things like this can be important in geology because as this decay occurs, with the gamma decay, you can get a significant amount of heat being generated. That's a good insight. Thank you. Anybody else?